Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, we are going to look at a couple of examples related to MM1 queuing systems. Okay, let's look at the first example. In this example, we are looking at a gas station. In this gas station, on average, we receive 7.5 customers per hour that come to fill their tank. And in this gas station, there is only one pump. It takes on average 4 minutes to provide service to a car, and we assume that inter-arrival times and service time all are exponentially distributed. So this is definitely an example of an MM1 queuing system. So in the first piece of information, it tells you that on average 7.5 cars or customers per hour come to the system to get their gas. So this is definitely lambda, the rate of arrival of customers to the system. That's 7.5 customer per hour. And then in the next bullet, it tells us that it takes on average 4 minutes to provide service to a car, right? So this is service time. This is the time spent in the server. This is the service time, and this is 4 minutes. So pay attention that this is not service rate. If it was service rate, the information would be like, oh, we provide service to, for example, 10 cars per hour. So the service rate always have unit of time, number of cars per hour. However, what is given to you is the service time, which is 4 minutes. So we have to calculate the service rate ourselves. So how do we calculate the service rate? If you remember from the formulations that we developed previously, we had that WS equals to 1 over mu. So then if we need mu, it's going to be equal to 1 over WS, and that's equals to 1 over 4 customers per minute. And I do want to have the rate of mu and lambda to be similar. If the lambda is number of customers per hour, I do want to have the same unit for mu as well. If I want to translate this to number of customers per hour, I'm going to multiply it by 60 minutes per hour, and that is going to be 15 customers per hour. Which also makes sense. If it takes 4 minutes to provide service to each customer, then in 1 hour, we can provide service to 15 customers. So the numbers make sense. So in the first question, we are asked to calculate L and W for this system. L is average number of people in the system, and W is the average time that these customers or cars spend in the system. So the formula for L is rho over 1 minus rho. Rho equals to lambda over mu. Lambda is 7.5, mu is 15. So this is going to be 1 over 2 or 0.5. That's the value of rho. If I put that value in the formula for L, this is going to be 0.5 over 1 minus 0.5 equals to L. So on average, there is one customer or one car in the system. Then the formula for W, which is average time a car spends in the system, is L over lambda, which is going to be 0.13 hours. So in this system, the cars go to fill up their tank when their tanks are half full. So this rate of arrival is related to the scenario when the cars go to the system when their tank is half full. Now let's assume a panic situation has happened in the city and the cars are going to fill their tank when their tank is 3/4 full. So in previous scenario, they would go to fill their tank when their tank is half empty, but in this scenario they go to fill their tank when their tank is 1/4 empty. So then we can say that basically the rate of arrival of the cars or customers to the gas station has been multiplied by 2. So then the rate of arrival to the system in this scenario is going to be 7.5 multiplied by 2, which is 15 cars per hour. Also, since the cars need to only fill 1/4 of their tank, the time that they spend in the gas station is less. So previously it would take them 4 minutes to fill their tank. Now it takes them 3 1/3 of a minute to fill their tank. So again, their service time is 3 minutes and 1/3, or 10 over 3 minutes. As a result, their service rate is 1 over service time, which is 1 over 10 over 3. That's going to be 3 over 10 minutes. So if I want to calculate service rate, is going to be 1 over service time, which is 1 over 10 over 3. So that's going to be 3 over 10 cars or customers per minute. And again, if I want to translate the unit of time to customers per hour, I have to multiply it by 60 minutes per hour. And that's going to be 18 customers per hour. Now, in this new setup, what is the value of L, which is number of cars in the system, and what is the value of W, which is the time that the cars will wait in the system. So L equals to rho over 1 minus rho. Rho equals to lambda over mu. It's going to be 15 over 18. That's going to be 5 over 6. So here then 5 over 6 over 1 minus 5 over 6. That's going to be 5. So after the panic situation happens, cars come to the system more often to get their tank filled, and the number of customers or the number of cars that are in the system is going to increase and go from 1 to 5. The value for W, which is the time waiting in the system, is going to be L over lambda. That's going to be 1/3 of an hour or 20 minutes. So not only the number of cars or customers in the system has increased, but also the time waiting in the system has increased. So the panic situation has caused more customers to be in the system, and they spend more time in the system. In the next example, we are going to look at the security check of an airline. So in this security check, on average, we are going to receive 10 customers per minute that are going to do the security check. There is one security checkpoint in this airport, and this security checkpoint is going to process 12 customers or 12 passengers per minute on average. So the service time for each, or the time for the security check of each passenger, is also exponentially distributed. Similarly, we know that on average 10 passengers per minute arrive to the system, and the inter-arrival times are also exponentially distributed. And one other thing that we know about the system is that this system has only one checkpoint, which has one X-ray machine and 2 people that are working in the area. However, there is only one checkpoint. No matter if there are 10 people working or 2 people or 1 people, there is one checkpoint that provides service to the passengers. So the structure of this problem very well falls under the category of MM1. The inter-arrival time and the service times have exponential distributions, and there is one server in this system. Now, what is given to us? So on average, 10 passengers per minute come to get their security check done. So that's lambda, which is 10 passenger per minute. Also, we know that the checkpoint can process 12 passengers per minute. And so that's our service rate, which is 12 passenger per minute. Now, in the first question, we want to see what is the probability that a passenger has to wait before being checked at the security check. These questions are important because, as you can see here, I'm not telling you explicitly what you need to calculate. I ask you some questions, and then in answering those questions, you have to figure out what you have to calculate to be able to answer that question. So here I'm asking you, what is the probability that a passenger who comes to the airport has to wait in the security check? So what would be the conditions under which a passenger has to wait? A passenger has to wait definitely if there is one customer in the system with probability of pi1. If there is one passenger in the system, for sure that person will be in the security check, right? That person is being checked. So if then another person comes in, that person for sure has to wait in the line till the person at the security check is done. So if there is one person already in the system with probability of pi1, for sure a new person has to wait. How about if there are 2 people in the system with probability of pi2? If there are 2 people in the system, for sure one of them is at the security check, one of them is waiting in the line. So if a new person comes in, that person should definitely wait in the line before it can be checked. How about 3 people in the system? That's the case as well. One person is in the security check, 2 people are in the line. If a new person comes in, that person has to definitely wait in the system before that person is being checked. And this goes all the way for P4, P5, all the way to P infinity. So then the probability that a person that comes to the system has to wait before that person is being checked is when there is one person in the system, or there are 2 people in the system, or 3 people, or 4 or 5, all the way to infinity. So this sum basically is giving me the probability that the person that comes to the system has to wait in the system before that person is being checked. What is the value of the sum of these probabilities? We know that pi 0 plus pi 1 plus pi 2 all the way equals to 1. So if pi 0 is not included in this sum, then this sum will be 1 minus pi 0. So to be able to find the answer to this sum, all I need to calculate is 1 minus pi 0. And pi 0, if you remember from the formula that we calculated for an MM1 system, pi 0 is 1 minus rho. And so then this sum is going to be 1 minus pi 0, 1 minus rho, and it's going to be rho, and rho equals to lambda over mu, and the lambda is 10, mu is 12. So this is going to be 5 over 6. That would be the probability of having a person or a passenger that comes to the system has to wait before that person is being checked. And before we go to the second question, basically, let me just give you another example related to the first question. So if I ask you, what is probability that the person that comes to the system does not need to wait? Then to be able to answer this question, so you have to think about what would be those scenarios in which a person or a passenger that comes to the system does not need to wait. So a passenger does not need to wait only if there is 0 people in the system. When there is 0 people in the system, the passenger that comes immediately goes to the security check and the person is not going to wait at all. So the probability that a passenger does not need to wait before he or she can do the security check is when there is no person in the system, and that happens with probability of pi 0, which is 1 minus rho, 1 minus 5 over 6, which is 1 over 6. So that would be the probability that a passenger that comes to the system can go to the security check directly without waiting in the system at all. So those are the scenarios in which as I told you, I'm not telling you exactly calculate pi 0 or pi 1 or pi 2, but I asked you a question, and then in answering that question, you have to think about what is the thing that you have to calculate to be able to answer that question. And in this example is pi 0. Okay, now let's go to the second question. On the average, how many passengers are waiting in line to enter the checkpoint? So how many passengers are waiting in line, right? So that's LQ, number of people that are waiting in line, that's LQ. We calculated the formula for LQ for an MM1 system, and that's rho square over 1 minus rho. And given the fact that rho equals to 10 over 12 or 5 over 6, then LQ is going to be 25 over 36, 1 minus 5 over 6. And that's going to be 25 over 6 passengers. So this is average number of passengers that are waiting in the queue to finally get their security check done. One other question that we can ask about this system is that, for example, on average, how many people are at the security check of the airport, like in the system? So when I say in the security check of the airport, I mean the system overall, the queue and the service area. So here, then I need to calculate L. And the formula for L is rho over 1 minus rho. That is going to be, and if I want to calculate the time that these passengers wait in the whole system, in the whole security part of the airport, security check part of the airport, that's going to be W. The whole time that the passengers need to wait in the system before they are finally done, that's going to be W, which is L over lambda. That is going to be 1 over 2 minutes. Note that here the unit for L is passengers. P, the unit for lambda is number of passengers that come to the system per minute. So if we divide these units, then whatever is going to be left is minute. So then the unit of W here is half of a minute. So basically the passengers can come to the system, go get their service and leave in half of a minute, which is quite fast. Queuing systems also can be used for analyzing different type of systems which may not immediately feel like they have the structure of a queuing system. However, we can still use the formulas for the queuing system, and we can analyze those type of systems. So let's look at one example. So here we are looking at McDonald's. So McDonald's receives an average of 10,000 pounds of potatoes per week to be able to provide the food and everything. On average number of pounds of potato that they have on hand is 5,000 pounds. So 5,000 pounds is in the restaurant at any point of time. On average, how long do potatoes stay in the restaurant before being used? Okay, so here we can look at this actually as a queuing system. We can say that, okay, this 10,000 per pounds of potatoes per week that come to the system is our lambda, which is 10,000 pounds per week. And then when it says the average number of pounds of potato on hand is 5,000 pounds. So these are number of pounds of potatoes that are in the system. So this can be treated as L. And then lastly, when it says on average, how long do potatoes stay in this restaurant, in the system, before they are being used? So we basically need to calculate W, which is L over lambda. That's going to be half a week. Again, to find the correct unit of time, just pay attention that here L, the unit of time for L is pounds, and the unit of time for lambda is pounds per week. So then the unit of W, which is the time that these pounds of potatoes stay in the system, is going to be week.